The project is entitled Soft Goods Isolation Device Experimentation, SIDE, for Lunar Habitat Seismic Resiliency. Now, does the moon actually have seismic hazard near the future moon base? These are unanswered state-of-the-art questions. The Apollo missions made significant contribution in attempting to address this, but the overall conclusion is that there is not enough data to accurately characterize the envisioned landing sites. This means that we don't know what type of seismic wave can affect the habitat, if any. Now, how can we make our habitat resilient against such unknown seismic events?
SIDE will answer these questions. SIDE is an inflatable device that is intended to act as an air spring isolator. Its design consists of a pressurized air bladder that is sandwiched in between two steel plates connected through a clevis pin-type coupler that provides support to the restraining layer. The restraining layer is composed of Vectran straps with a plain weave pattern, consisting of both axial and hoop straps. Additionally, a thermal protection system for the outer layer is included for isolating the inner layers from the thermal fluctuations on the lunar surface. The purpose of SIDE is to reduce the vibrations transmitted from the lunar surface into the lunar habitat. Extra focus will be placed on studying the vibrational dynamics of soft goods with regards to lateral stiffness. Primary testing will be focused on characterizing the device for lateral motions, but vertical motions are also considered.
Our inflatable will start in a stowed position until landing. At the first deployment, the pressure inside SIDE will increase, inflating to raise the entire habitat. Through solving the fundamental equation of motion from the general load analysis, we can observe the transmitted acceleration to the habitat due to input signal frequencies. The top chart in red shows the input signal with the transmitted acceleration seen in green. In blue is the pressure of the soft goods devices starting from an initial pressure, which adjusts depending on input. At the beginning of the experiment, there is an initial uptick in transmitted acceleration. However, the system automatically adjusts the pressure of the devices to change the dynamic properties of the system, reducing the transmitted acceleration to the habitat.
This means that SIDE will provide dynamic adaptability to the system, that despite variation in frequency content and amplitude of the input motion, the habitat will experience a reduction in transmitted acceleration. As shown in the middle, we observe the response of the structure without SIDE, and on the right, the response of the structure with SIDE. It is evident that the habitat on top will remain undisturbed with the implementation of SIDE.
We propose to design and manufacture 3 prototypes, which will undergo dynamic and vacuum tests simulating the not so well-known seismic lunar environment and the vacuum conditions on the lunar surface. The seismic environmental test will be performed using a shake table. The specimen will be subjected to a lateral ground motion. The test protocol includes changing the pressure to measure the behavior of the lateral stiffness of the device.
Finally, SIDE can be implemented for the rare kind of structures and is not limited to the one assumed. Thank you for your time.